Hello and welcome. This recording is session one of an eight-part series on the topic Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstobitoff. I'm a structural engineer focusing on earthquake engineering. This series of recordings is part of the MBAR initiative by BC Housing. It includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. This session is titled Understanding Code-Level Earthquake Design for New Buildings. It will set the basis that the other sessions will build from. Briefly, the other 7 sessions will address performance-based design, seismic isolation, supplemental energy dissipation, some mini case studies regarding costs, habitability, which is more than just structural design, some considerations for existing buildings, and earthquake instrumentation. So what codes am I referring to? It's the Vancouver Building Bylaw, the BC Building Code, and the National Building Code of Canada, with the current additions noted. The National Building Code of Canada is the model code that is used by the other 2 codes. The earthquake design provisions are the same in all these codes. And what buildings am I referring to? They're called Part 3 buildings in the code. So these are larger buildings, more than 3 stories in height, more than 600 square meters in building area of the occupancies noted, or buildings of any size or height that are assemblies, care facilities, or high hazard buildings. Part 4 of the codes is the structural design for Part 3 buildings. So this talk today does not address Part 9 buildings, which are small buildings, less than 3 stories, smaller area of the residencies and occupancies noted. A few aspects of earthquake design. The design is for one hazard level only, a very rare and severe earthquake. 2 ways of addressing its probability. One is a probability of exceedance of 2% in 50 years, or an annual exceedance probability of 1 over 2475. The map on the right shows the hazard levels within BC. The red indicating the areas of highest hazard, and then with the gradation to more moderate hazard interior of BC in the lighter green and blue shades. The code addresses 3 different potential earthquake sources in BC. The large subduction magnitude 9 earthquake just off the west coast, the subcrustal or in-slab earthquake with a magnitude of around 7.5 at a modest depth, and a shallow crustal earthquake with magnitudes 7+. A key aspect of the current codes is that they are objective-based. For earthquakes, the fundamental objective is structural safety, to protect the life and safety of building occupants and the general public. And for normal importance buildings, this means being able to egress the building safely. The code groups buildings into 3 groups: normal importance, residential, commercial, with an importance factor of 1 and a drift limit of 2.5%. High importance buildings such as schools, with a higher importance factor and a lower drift limit. And post-disaster buildings such as hospitals, with the highest importance factor and a much tighter drift limit, where drift is the interstory deflection during strong shaking, which is 1 floor relative to the one below it. So the higher the importance factor and the lower the drift limit will result in the lower damage after the design level earthquake. So a few aspects about design of new buildings. The design is based on the building's weight, its fundamental period. There's 5 different material types, and it includes the amplification due to different soils. The key aspect in this discussion is that there are over 30 different structural systems that can be used, and they're all code compliant. And they're made up of different framing systems such as shear walls, bracing, and moment frame. And I'll speak more about this in a later slide. The 30 systems that I mentioned, the energy of the earthquake is dissipated by ductility or controlled damage of the system. And each of these seismic force resistance has a unique RD value, or a ductility-related factor, that can vary from 1.5 to 5. So the lower RD value means less damage and less residual drift after the earthquake. And the higher RD value is more damage and the potential for more residual drift after the earthquake. Many new buildings are designed with a high RD value because that involves a reduced and lower cost at the time of design, with the trade-off of more damage and more repair cost after the design level earthquake. So back to some of the performance objectives for the three groups of buildings. So again, in the normal performance buildings, it'll minimize loss of life, extensive structural damage, but it retains a margin of resistance against collapse. The higher importance buildings, a higher degree of safety, and less damage. The objective being immediate occupancy or the ability to shelter in place after the earthquake. And post-disaster buildings with an objective to remain functional. However, the code clearly states that the mere application of this importance factor will not necessarily ensure the operational readiness of the facility after an earthquake. To ensure that, a detailed study needs to be carried out. This graphic indicates or illustrates the variability of performance due to the different building types. You can see the cartoons of the different levels of damage of a building, and the lines showing damage or loss from green to little loss to red of a significant loss, and the time out of service. And the three bars of the three importance factors shows the variability, with the bar moving to the left each time for lesser damage and less time out of service. But the variability is due to the 30 different building types or SFRS systems that I discussed earlier. So an example, in Chile, a magnitude 8.8 earthquake. This is a normal importance building after that earthquake. So to the naked eye from the outside and from a distance, appears to have no damage, no broken glazing. However, upon closer inspection, extensive damage. Every concrete spandrel was damaged, requiring significant repair time and significant repair cost. It met the code requirements of life safety. All occupants exited safely from the building. So this is the quick summary of today's session. What the building code does is it sets the minimum legal requirement for new buildings. It has an objective of life safety in all cases, and it does provide other objectives for some damage control in the two other groups of buildings. It does not provide an earthquake-proof or damage-free design. It does not provide information on damage state, repair costs, or repair time. The result, due to a wide range of possible building characteristics, site conditions, different seismic force resisting systems, irregularities, a wide variation in the extent of damage can be expected. The next session will touch on performance options and options to design better than code. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and web page address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.